Hello everyone, welcome to the PYQ series of my YouTube channel SGKmistry lectures. In this video, I'll be explaining how to solve various questions on physical chemistry, and all these questions have been selected from the question papers of the various competitive exams from the past few years. Let us look into the upload timetable. So as I already told, I'll be uploading 10 videos in the duration of 10 days. Already 8 videos have been uploaded in my YouTube channel. The links for all these 8 videos have been provided in the description box. The first 4 videos are mainly based on organic chemistry. The next 3 videos are based on inorganic chemistry. And the last 3 videos of this particular PYQ series are exclusively based on physical chemistry. Let us start with question number 1. For a first order reaction, A gives products. Initial concentration of A is 0.1 molar, which becomes 0.001 molar after 5 minutes. So this is A minus X. This is initial concentration A. And it has been given that it becomes the initial concentration 0.1 molar becomes 0.001 molar. So this represents A minus X. How much is remaining after 5 minutes? So this is T, the timing. Rate constant for the reaction in minute inverse. So what is K? That is what you need to find out. So we know that for a first order reaction, K is given as K is equal to 2.303 by T log A by A minus X. Now we have 2.303 by time is 5 log of A is 0.1, A minus X is 0.001. Now I can shift the points here 1, 2, 3. So here also I have to shift to 3 points 1, 2, 3. So it becomes log of 100. So we have 2.303 divided by 5. Log of 100 is nothing but 2. So we have 2.303 into 2 divided by 5. So now I can take it as 2.303 into 2. 2 3s are 6, 0, 6, 2 2s are 4. So we have 4.606 divided by 5. I can shift the points here. Here also I shift the points. So 4606 divided by 5000. So I can again cancel it out. 2, 3, 0, 3, 2, 5, 0, 0. So 2303, 2500. So this is how I do the simplification. Now, we know that 2500, it is 0 times. So here I have 23030. So now it will be, if I take 2500 into 9, 9 5s are 45, 18, 2, 2, right? So 0.9. So it will be 22500. So I got something with 0.9. So you can see here in the options, we have 4.6, 0.9, 0.4, 0.2. So without going for further calculations, you can easily select the answer 0.9212. So here you're going to get 0.9212. So option B is the right answer. So once you get the starting digits which are required, which is enough to differentiate the options and select the correct answer from the given options, you can stop the calculations there itself and select the option to avoid spending more time on a particular question. Let us go to question number 2. At 30 degrees Celsius, the half-life for the decomposition of AB2 is 200 seconds and is independent of the concentration of AB2. So here the half-life is independent of the concentration of the initial concentration of the reactant. So it shows that the reaction is of the first order. Now, the time required for 80% of the AB2 to decompose is, so they are asking how much is the time required for AB2, that is the reactant, to decompose 80%, to 80% of that reactant to decompose, how much of the time is required. So now we know that for first order reaction, T half is given by 0.693 by K. So we have T half is already given 200 seconds. So I can write it as K is equal to 0.693 by 200. So I have the value for K. I'll do the simplification later. Now, for 80% decomposition, 80% decomposition, because this is what we have to find out. So we have A by A minus X is equal to, so initial concentration, if I take it as 100, for 80% decomposition, once the 80% has been decomposed, what is A minus X? How much is remaining? 20 is remaining because 80 has been decomposed. So I have 1s are, 5s are. So I have this value as 5. So I have to write it as T is equal to 2.303 by K. Log of A by A minus X is nothing but, now it is 5. Now, here given values are log 2 is 0.30 and log 3 is given 0.48. So now it is, we have got log 5. So log 5 can also be written as, now 2.30 by K, I can also write it as 10 by 2. So log 10 by 2 is nothing but log 10 minus log 2. So I have 2.303 by K log 10 minus log 2. So we have log 2 is nothing but 0.30. So log 10 is 1. Log 2 is 0.30. So I have the value as 0.70. So this value will be 0.70. Now K value we already have here 0.693 by 200. So I can substitute the value. So 2.303. K value is 0.693 by 200. So 0.693. 200 will go to the numerator. Now log 10 minus log 2, I have got the value here 0.70. So now there are 3 digits after the decimal point in the denominator. So I'll do the shifting of points here so that the calculations will be easier. So I have here, I shift 2 points and I also shift one more point here so that it becomes 230.3 into 200 into 7 divided by 4. So this also I'll shift it. So it comes as divided by 693. So let me just try 230 into 3.3 into 7. So 21, 7 threes are again 21, 14, 16. So we have 1612. Again this into 2. So 200 is there, but I'm for the calculation, I'll just take it as 2. 2 twos are 4, 2, 12, 3, right? So we have 3224.2 into 10 to the power of 2 divided by 693. So now, while doing the calculation, you can easily see that here 3224. I'll just take the round of digits 693. So now if you look into it, so if I take 693 into 4, 9 into 4 is 36. So 37, 24, 27. So we have 4, 2, 7, 7, 2, 2 here, 5, and then we have here 4, right? So next it is not divisible. So I have to put a point. Then I put a 0 here. So now you just look here. There is 4 and also there is a 10 to the power of 2 which is there. So that means it is something like 4 point something into 10 to the power of 2. That means I have to shift the points 2 times. So something with 400, right? So look at the options here, 267, 532, 466, 322. So the answer should be 400 something. So we have already 466 as the option. So I'm not going to divide it further. So I can stop the calculations here itself because I already got the answer. So option C is the right answer. So you're going to get here 4.66 into 10 to the power of 2, which is nothing but 466. So coming on to question number 3. For a first order reaction, the time required for completion of 90% reaction is X times the half-life of the reaction. So you need to find the value of X. So for 90% completion, so again, it is mentioned that it is first order reaction. So time is equal to 2.303 by K log of, so again 90% completion. So A is 100, 90% has been completed. So how much is remaining? 10 is remaining. So 1s are, 10s are. So T is equal to 2.303 by K. Now log 10 is 1. So I'm not going to write anything. So for T here, for 90% completion, we have 2.303 by K. Now, For T half, we have the equation T half is equal to 0.693 by K. So now what is given for this particular reaction? The time required for completion of 90% reaction is X times the half-life of the reaction. So what I have to write? So 0.693 by K, this is the half-life of the reaction. If I multiply this by X, that is equal to the time required for the 90% completion of the reaction. So what is the time required? We got it here, 2.303 by K. Now K and K cancels. So X will be 2.303 divided by 0.693. So you can shift the points 3 times. Here also I shift the points 3 times. So I have 2303 divided by 693. So now if I take 693 into 3 times, 27, 18, 19, 20. So I have 3 times 2079. So I take it here, 9, 4, so 2 here and 2 here, right? So I put a point here and then continue. So now look at the values which are given in the options. So easily we can select what is the answer. I got something with 3 point. So here we have 3.32. So obviously you're going to get 3.32 here if you go for further calculations. So I'm not going further for the other calculations because already we have got the answer, that is 3 point something. So 3.32 is option C. So I'm not going to waste my or use further time for the calculations. So I'm directly going to select the option, that is option C, which is the right answer. Okay. Yes. Coming on to question number 4. The slope of Arrhenius plot of ln K versus 1 by T of a first order reaction is -5 into 10 to the power of 3. Okay. K. So the value of EA for the reaction is. So now we have, this is the graph. So if you plot a graph of ln K versus 1 by T, so we have the slope like this. Now this intercept value is, it is the ln A. So we are not going to worry much about this particular thing because we are not interested in this part. We are only interested in the slope. So slope is equal to minus EA by R. So now we have minus EA by R is equal to, so we are only interested in the slope. So I'm not going to worry about this. So only what is x-axis, what is y-axis, as well as what is present in the slope. So minus EA by R is the slope. Now slope value is already given here in the question. That is equal to -5 into 10 to the power of 3. So minus EA is equal to -5 into 10 to the power of 3 into R value has been given, that is 8.314. So we have 8.314 into 5. So 20, 5 ones are 5, 6, 7, 15, 40, 41. So we have 41.5. So minus and minus cancels. So EA is equal to 41.5 into 10 to the power of 3. Or I can also write it as 41.5. This is nothing but joules per mole. So 10 to the power of 3, I can also write it as kilojoules. So kilojoules per mole. So we have the answer, that is option B, 41.5 kilojoules per mole. Next, coming on to question number 5. For a reaction of order N, the unit of rate constant is. So to find the unit of the rate constant, formula which is used is, it's very simple formula. We take concentration by time into 1 by concentration to the power of N, where N is the order of the reaction. So this is what we need to use for finding the unit of the rate constant for the given reaction of a particular order. So now nothing is mentioned about the order, like what is the order? It is just given as order of N. So I'm going to take it as N itself. So concentration is given as mole per liter. Time is expressed in second. So we have 1 by, here concentration to the power of N. So it will be mole to the power of N per liter to the power of N. Now, if I bring it above to the numerator, now this will be as such mole per liter. Second, I bring it above, so it becomes second inverse. Now, this mole, it comes above, so it will become minus n. And now let me simplify here itself instead of going for another step. So now you see here, this indicates mole to the power of 1, right? Now n is in the denominator. When I bring it up, it becomes 1 minus n, right? This n becomes minus n when it comes to the numerator. Already there is 1, that is mole to the power of 1. So overall you get 1 minus n. So mole to the power of 1 minus n. Now talking about liter. Liter, already there is minus 1 in the numerator. Now this minus 1, when I bring it above, it becomes plus, right? So it is minus n here, minus 1 into n, because it is to the power of n, so it will become minus n. But now when it comes to the numerator, it becomes plus n. So L to the power of n. Now when I combine this, it will become L to the power of n minus 1. So I'll do the changes here itself instead of writing one more step. So I have L to the power L to the power of n minus 1, because n was in the denominator, that was minus n. When I bring it to the numerator, it becomes plus n. So I have mole to the power of 1 minus n, L to the power of n minus 1, and second inverse. So this is the unit of the rate constant for a reaction of order n. So we have the options here: mole to the power of 1 minus n, L to the power of n minus 1, and second. So this cannot be the answer. Mole to the power of 1 minus n we have here, L to the power of n minus 1, second inverse. Yes. So we have option A as the right answer. Next, question number 6. So one reaction has been given: A plus 2B gives 2C, 2 moles each of A and B present in 10 liters of the solution. So total there is 10 liters of the solution. So in this 10 liters of solution, 2 moles of A and B are present. So which is the initial concentration? So first let us write whatever is given. So initial moles in 10 liters of the solution. So we have A, 2 moles, B, 2 moles, and C, nothing is present because C is the product, right? So first, initially, C is not present. So C is 0 moles. That is in the initial concentration. When we are talking about initially, how many moles were present. Now, what else is asked? You have to find the Kc for this reaction. And the equilibrium reaction also has been given. A plus 2B gives 2C. Right? Now, let us take the extent of the reaction. Extent of the reaction to be X. Okay. So now we have for 2 moles of C. So 2 moles of C is formed. So 2X is formed, right? So let me take 2X is equal to 1. So X will be 0.5. Right? In the reaction, we can see that due to the extent of the reaction, we get 2 moles of the products that are formed. So 2X will be equivalent to 1. Then we get the X value as 0.5. Now we can calculate based on this the equilibrium moles. That is the moles of the reactant as well as the product, that is A, B, and C at equilibrium. So for A, I can write it as 2 minus X. Initially it was 2. Now because of the extent of reaction, that is X, how much of A is present at equilibrium? So X is nothing but 0.5. So 2 minus 0.5, I get it as 1.5. Now for B, again, 2 minus, now it is 2B, right? What is there in the equilibrium equation? So we have 2 minus 2X is equal to 1. That is 2 minus 0.5 into 2, that is 1. So 2 minus 1 is 1. So next, talking about C, C will be 1. So now, let us talk about equilibrium concentration. Equilibrium concentration. Okay. So for A, so concentration of A, how do we find out? So number of moles we have 1.5 divided by 10. So total volume of the solution that was taken is 10 liters. So number of moles by the volume of the solution, that will give you the concentration. So 1.5 by 10 will give you 0.15 moles. Same way, I can also calculate for B. So B, we have the moles here, that is 1. So 1 divided by 10. So we have 0.1 molar. For C, we have 1 divided by 10. So here also we have 0.1 molar. So this is the equilibrium concentration. So now finally, we have got the equilibrium concentration, which is required to find out the Kc. So Kc is given by, so this we already know, very simple. So C square divided by concentration of A into concentration of B, again square because of the coefficient. So now the concentration of C at equilibrium is 0.1. So 0.1 square divided by concentration of A is 0.15 into concentration of B is again 0.1. So 0.1 square, right? So 0.1 square and 0.1 square will cancel out. So we have 1 by 0.15. So shift the points, right? So we have 100 by 15. So we have 15 into 6, 6 5s are 30, 6 1s are 6, 90. So we have 6 are 90, 10 here. So then it again continues, right? So again 6 are 90 and then it goes on. So 6.666, what you're going to get. So it can be rounded off to 6.67, right? So we have the answer option B as the right answer. That is 6.67 is the value of the equilibrium, the Kc, okay, for this particular reaction. Next, question number 7. 5 moles of liquid X and 10 moles of liquid Y make a solution having a vapor pressure of 70 torr. So this is the total vapor pressure after mixing both of these liquids. So based on 5 moles and 10 moles, they have mentioned separately. So after mixing them, the pressure, the vapor pressure when it is measured, it comes up to 70 torr. The vapor pressures of pure X and pure Y are 73 torr and 78 torr respectively. So this represents the P naught. P naught values. So this is for X and this is for Y. Because they have mentioned it is the vapor pressure of the pure X and pure Y, right? So which of the following is true regarding the solution? So first let us calculate. We need to find out whether the the pressure under the ideal conditions and the observed conditions, how it is related to each other. Now for an ideal solution, we have, let us calculate the mole fraction of X. Let me take it as X, the capital X, or you can also take it as small letter x for X. I take it as small letter x because to avoid the confusion with this X and the mole fraction X. So we have here the number of mole fraction is nothing but the number of moles of that particular component divided by total number of moles in the solution. So now for X, we know that the number of moles of that component is 5. Total number of moles is 10 plus 5, that is 15. So we have 1 by 3 as the mole fraction for X. Same way, I can also write the mole fraction for Y. That is, the number of moles of Y is 10. Total number of moles is 10 plus 5, that is 15. So 2 by 3. So this is the mole fraction. Now we know that P is equal to the total pressure is equal to mole fraction of X into the pressure, that is pressure of the vapor pressure of the pure component, that is P naught X plus again XY, that is a mole fraction of Y into the vapor pressure of the pure component, that is the vapor pressure of the pure component of Y. Now we have the mole fraction here. I'll substitute the values 1 by 3 into, here we have for pure component that is 63 plus we have here 2 by 3 into for the pure component we have 78, right? So now we have 3 ones are, 3 twos are, 3 ones are, right? Then we also have here 3 ones are, 3 twos are 6, 3 6 are 18. Now here it is 21 and here 26 into 2 will give you 52. So we have 3 and 7. So 73 torr. So this is for the ideal solution. So 73 torr should be the calculated value. According to the calculations, according to the ideal solution conditions, this should be the pressure, that is 73 torr. But what is the observed pressure? Observed vapor pressure is 70 torr, right? So observed is 70 torr. This is the observed vapor pressure. So now the vapor pressure that is observed is less than the vapor pressure of the ideal solution under ideal conditions if you are considering. So if there are no interactions or if delta V of mixing is zero, all that, when we are considering those conditions, then the vapor pressure of the observed vapor pressure is lesser when compared to that of the pressure under ideal conditions. That is when you consider it as an ideal solution. So now it is very clear that since the observed pressure is lesser, it shows the negative deviation from the Raoult's law, right? Because the observed value is lesser. Now let us look into the options. The solution has volume greater than the sum of the individual volumes. The solution shows positive deviation. The solution shows negative deviation. So we already have the option based on whatever we have got as the answer. So yes, option C is the right answer because here we know that the observed vapor pressure is lesser, which shows that this particular mixture of solution shows the negative deviation from the Raoult's law. Coming on to question number 8. In which of the following equilibria Kp is not equal to Kc? So in this case, we need to look into the relation, that is Kp is equal to Kc into Rt to the power of delta Ng. Now delta Ng is nothing but delta Ng is equal to moles of gaseous products minus moles of gaseous reactants. Okay, so we are not only interested in this particular delta Ng term from this equation. Okay, so now if delta Ng is equal to 0, then what is going to happen? This becomes Rt to the power of 0, which becomes Rt equal to 1. So then if this happens, if delta Ng is 0, then Kb will be equal to Kc, right? So we have this particular this relation between Kp and Kc. Now, if delta Ng, that is the power, if it becomes 0, if it is 0, then Rt becomes 1, then Kp becomes equal to Kc, right? So that's why I've taken this equation and explained. Now, let us calculate the delta Ng for all of the given options. Then we can identify where Kp is not equal to Kc. Now, finding for A. So, here, see, delta Ng is number of moles of gaseous products minus moles of gaseous reactants. So in the products, how many gaseous moles are there? Here 1 and 2. So we have 2 minus in the reactant, how many are there? 2. So we have 0. So delta Ng here is 0, which indicates Kp is equal to Kc. Okay. So they are asking where Kp is not equal to Kc. Now in the second equation, we have again, see, both are gaseous state, in the gaseous state. So number of moles is 2 in the product side. In the reactant side also, again, it is in the gaseous state and there are 2 moles. So 2 minus 2 is equal to 0. Again, here, delta Ng is equal to 0. So Kp is equal to Kc. Coming on to option C. See, in the product, there are 2 moles minus in the reactant, this is in the solid state, so I cannot consider that. We are only looking into the gaseous reactants or gaseous products. So in the reactant, I have only 1 mole of the gaseous reactant. So 2 minus 1 is 1. So here, delta Ng is not equal to 0. So in this case, we have Kp, which is not equal to Kc. So we have the answer, that is option C. Let us also confirm with the option D. So we have here in the product 1 and 1, both are gaseous. So 2 minus in the reactant, again there are 2 moles of the reactant. So 2 minus 2 is equal to 0. So here also delta Ng is equal to 0, which means Kp is equal to Kc. Yes, coming on to question number 9. For the reaction, so one reaction is given where H2 and I2 react together to give 2 moles of Hi. So K value is also given, that is 47.6. If the initial number of moles of each reactant and product is 1 mole, this is the initial concentration, then at equilibrium, what is the relationship between the different, the concentration of the reactants as well as the products? So that is what is asked. So initially, First of all, let us try to write the equation for K. We have K is equal to concentration of HI square divided by concentration of H2 into concentration of I2, which is equal to 47.6. This is already given. Now, initial concentrations. So, initial concentration will be concentration of H2. It is a reactant, right? So, it is 1 mole. Again, the concentration of I2, that is also equal to 1. So, 1 mole. And HI is equal to 1. So here you can see if the initial number of moles of each reactant and product. So that is also mentioned here about the product also. So that's why I'm taking even the concentration of HI as 1 mole, because since it is mentioned in the question itself that even the product is taken as 1 mole. Now at equilibrium, so we know that at equilibrium, what is going to happen? H2 is equal to I2. Let us take it as X. Okay. So at equilibrium, we are just taking it as the concentration of H2, which is equal to the concentration of I2, which will give X, because both of them react together in equal proportions to give HI as the product, right? So if 1 mole of H2 reacts, 1 mole of I2 is also required to react with H2 to give the product. So that is how you need to remember. If 0.5 mole of H2 reacts, 0.5 mole of I2 is also required. So 0.5 mole of H2 is used up. Even I2 also 0.5 mole will be used up so that to give the product, that is HI. So let us say that at equilibrium, the concentration is taken as X. Now, let us take the concentration of HI as Y. Okay. Now, let us try to write the equation for K. So we know that here HI square is there on the numerator. So I have to write Y square divided by H2 and I2, the concentration. So X, both of H2 and I2, it is taken as X here. So X into X will be X square. Now this is equal to again 47.6 because the K value has already been given. Now, we know that if you're going to take y by x, that is nothing but square root of 47.6, which is approximately, so it is equal to 6.9. Okay, so the square root of this particular 47.6 is 6.9. Or if you're finding it difficult to find the square root, you can see that in this case, it is lying between the square root of 49 and square root of 36. So square root of 49 is 7. Square root of 36 is 6. So the value of this particular square root will be somewhere between 6 and 7. So we are not interested into the specific value here because no calculations have been asked. So if you want, you can try finding out the square root or just you can leave it as such. Now from this, what we need to infer, that is very important. So we know that y by x is equal to 6.9, or if you don't want to find it, if you don't want to do the particular calculations for finding the square root, you can just leave it like that. We know that the value is somewhere between 6 and 7, right? So that indicates, this particular equation indicates that here it is very clear that y is greater than x, correct? Because y is equal to x into 6.9. So that means y is greater than x. So that means the concentration of HI is greater than the concentration of H2, which is equal to the concentration of I2, right? So this particular equation or this particular relation is very important for us to identify what is the relation between the various concentrations of the reactants and the products at equilibrium. So let us look into the options that are given. Now it is very clear that concentration of HI is higher and these two are equal. So here let us look into the options. Yes, so we have concentration of HI is higher than I2 and concentration of I2 is equal to concentration of H2, which is the correct relation between the concentration of the reactants and products. So we have option B as the right answer. Next, coming on to question number 10. Which of the given reactions is not an example of a disproportionation reaction? So here, in disproportionation reaction, as I've already explained, the reactant will form products in such a way that whatever the oxidation state of a particular element in the reactant is there, in the product, there will be two such products in which in one of the product, the oxidation state of that particular element is more, and the other product will have the oxidation state of that element which is lesser when compared to the oxidation state of that element in the reactant. Now, here, let us take the example. So, this decomposition of hydrogen peroxide is a very important reaction, which indicates it is an example of the disproportionation reaction. Let us also verify the same. So, here, O2 is there. It is peroxide ion. So, O2, 2 minus, right? So, here, in H2O, so O2, 2 minus in the sense, so per oxygen, if you consider, it will be -1. Now you see in H2O, here oxygen, the oxidation state is taken as -2, and for O2, we take it as 0. Now, in the reactant, that is -1, it is in between the oxidation states of the two products that are there, right? So in the product, the oxidation state of oxygen in one product is -2, and in another product, it is 0. So this -1 is in between these two oxidation states, that is -2 as well as 0. So this is a disproportionation reaction. So they are asking which one is not an example of a disproportionation reaction. Let us look into option B. So here, obviously, we are looking for nitrogen because there are two products with nitrogen. So you need to calculate the oxidation state of nitrogen. So hydrogen is taken as +1. Nitrogen, let me take it as X. Oxygen is -2. There are 2. So -4 is equal to 0. So X here, it will become -4 plus 3 becomes -3. So 0. So X is equal to +3. So let us look into this HNO3. So here +1 plus X -6 is equal to 0. So X is in the +5 state. Now here it is very simple. X is in the +2 state. So now you see here in the reactant, it is in the +3 state. In the product, it is in between +2, and the other product, nitrogen, is in the +5 state. So you can see this +3 is in between +2 and +5. So this is also an example of a disproportionation reaction. Now, it is very simple to identify, very easy to identify just by looking at the reactants. You can see that in option C, the MnO4 -2 is only forming one product with manganese in it, right? So just by looking at the reaction itself without calculating the oxidation state, you can identify which one is a disproportionation reaction. So next, coming on to the option D, just for clarity. So here Mn, I take it as X. Oxygen is -2. So -8 is equal to -2. Now this -8, if I take it to the other end, it becomes +8. So X is equal to +6. Here X -8 is equal to -1. So this -8, when I take it to the other end, it becomes +8. So it becomes +7 here. So X -4 is equal to 0. So X is equal to +4. So here also you can see +6 is in the reactant. Now in the product, we have two oxidation states for manganese, that is +4 and +7. So clearly this +6 is in between the two oxidation states, that is +4 and +7, right? So clearly option C is the right answer. Next, question number 11, calculate the energy in joules corresponding to light of wavelength that is given as 45 nanometer. Planck's constant is equal to H. So H value you should know, but most of the time it will be given. And speed of light also 3 into 10 to the power of 8 meter per second, which is given. So very simple. Here it's the direct substitution. E is equal to hc by lambda. So H, we already have the value 6.63 into 10 to the power of -34. C is also given 3 into 10 to the power of 8. Lambda is 45 nanometer. So 45 into 10 to the power of 9. -9, sorry. Okay, so nanometer. Now I can do the calculation. So 3, and here I can remove it. I can strike it off, and I can make it, I can simplify it 1 by 50. Now we have 6.63. Again, I will take the powers, and I can change the calculations. So now let us try to simplify the calculation. 6.63. Here it is divided by 15. So I can shift the points here. Here also I can shift the points. So 663 divided by 1500. So we have 663, 1500, 0. So here we have again 0. So 1500. So into 4, right? So that will give you 1500 into 4. So 6000. So we have 3. Again here 6. Now again it will be 0. So again I'm going to get 4, right? So 4 are again 6000. So 300 remains. And then it goes on. So here you get 2, right? So 3000. So 0. So you get here 0.442 into 10 to the power of. Now minus 34 is there, 8 is there. That gives you minus 26, right? So minus 26. Now if I take this minus 9 above, so here minus 26 plus 9, right? So here you get minus 19. So now if I shift the point this side, I'm going to get point. Now this is 0.442 into 10 to the power of minus 19 you get. Now if I shift the point here, I get 4.42 into 10 to the power of minus 18, right? So look at the options. Here clearly we have the answer, that is option D, 4.42 into 10 to the power of minus 18 joules. Since we are talking about energy, it will be joules, right? Next, question number 12. Of both an electron and helium atom is known within 1 nanometer. The momentum of the electron is known within 5 into 10 to the power of minus 26 kg meter per second. The minimum uncertainty in the measurement of the momentum of the helium atom is. So here it is, again, we know this is with respect to the uncertainty principle. So delta X into delta P should be equal or greater than H by 4 pi. So now we know that delta X is the same, right? So position of an electron and helium atom. So it is known within 1 nanometer. The momentum of the electron is known again within this particular value. So minimum uncertainty is asked. So delta X is the same. So delta P, the minimum delta P also will be the same. So here 5.0 into 10 to the power of minus 26 is given. So that will be the same as the whatever the measurement, the minimum uncertainty in the delta P. So delta P, whatever they are given, the uncertainty, that will be equal. So 5.0 into 10 to the power of minus 26 kg meter per second is the right answer. Next, question number 13. Uncertainty in position of an electron. So already mass of the electron is given. Moving with the velocity of 3 into 10 to the power of 4 centimeter per second, accurate up to 0.001% will be. So that is what is asked. So again, for uncertainty, we have to use h by 4 pi that they have given. So now, delta V is 0.001%, the velocity, right? So this is the accuracy of up to 0.001% is given. So 0.001% of how much? Of 3 into 10 to the power of 4. Now, if I calculate, I get it as 0.3 centimeter per second, right? So 3 into 10 to the power of 4 centimeter per second, accuracy is 0.001. So I'm going to find what is delta V. Now, delta X will be h by 4 pi into m into delta V. So now that m delta V is nothing but the momentum, right? So delta P will be equal to m delta V. Now delta V we already have, so multiply it by the m, the mass that is given. So 6.626 into 10 to the power of minus 27. Since it is given in a second, so that's why minus 27. Now 4 pi into mass of the electron is given 9.1 into 10 to the power of minus 28. Again, it is given in grams. So into what is delta V? It is 0.3. So when we do the calculations, we get it as 1.93 centimeter. So we have the option, that is option C, as the right answer. Just the calculations have to be done. This is the substitution for H they have already given. Now, since the change in momentum is not given directly, so we need to use P is equal to mv. So delta P will be m delta V, and then we do the substitutions. Coming on to question number 14. Which one is a wrong statement? Total orbital angular momentum of electron in s orbital is equal to 0. Yes, this is the right statement. An orbital is designated by 3 quantum numbers, while an electron in an atom is designated by 4 quantum numbers. Yes, because we have the spin quantum number also for an electron. The electronic configuration of n atom is 1s2, 2s2, 2px1, 2py1, and 2pz1. This is the wrong statement because the assigning of the electrons in px, py, and pz is just one possible arrangement. Okay, so it is not fixed. Whenever we are writing the electronic configuration, we are not going to write it this way. We are just writing 1s2, 2s2, 2p3. Okay, so this is the wrong statement. Next, the value of m for dz square is 0. So we have option C as the right answer. Next, question number 50. Which of the following is a wrong statement? The uncertainty principle is delta E into delta T greater than or equal to h by 4 pi. Yes. Next, half-filled and fully filled orbitals have greater stability due to greater exchange energy, greater symmetry, and more balanced arrangement, which is absolutely the right statement. The energy of 2s orbital is less than the energy of 2p orbital in case of hydrogen-like atoms, which is wrong. Because in case of hydrogen-like atoms, the energy of the 2s orbital is equal to the energy of the 2p orbitals. Okay. Next, the fourth one, de Broglie's wavelength is given as lambda is equal to h by mv, where yes, m is the mass of the particle, v is the group velocity of the particle, which is absolutely right. So we have option C as the right answer. Next, question number 16. Which of the following sets of quantum numbers represents the highest energy of an atom? So first one, let us see, n is equal to 3. Now we have L is equal to 0. So n is equal to 3. That means we have to write 3. Now L is equal to 0. So we have here 0, 1, 2, 3. This is for L. So for 0, it is S, P, D, F, and so on. Right. So now L is equal to 0. It shows that we are talking about 3S. Now let us also calculate N plus L here, which gives us a better idea about which one has the highest energy. N plus L is 3 plus 0, which is equal to 3. Next, here N is equal to 3, so 3. L is equal to 1, so we are talking about 3p here. So N plus L is 3 plus 1, which is equal to 4. Next, here N is equal to 3, so 3. L is equal to 2, so for 2 we have D, right? So 3 plus 2 here, that is N plus L, that is 5. Next, coming on to the last one, N is equal to 4, so 4. L is equal to 0, so S. So 4 plus 0, which is equal to 4. So it is very clear that here N plus 1 L value, it gives that is 5. We also know that comparing 3D and 4S, we know that 3D has a higher energy. So we have option C as the right answer. Next, question number 17. What is the work function of the metal if the light of wavelength 4000 angstrom generates photoelectrons of velocity 6 into 10 to the power of 5 meter per second from it? So mass of the electron is given, velocity of light, Planck's constant, and charge of the electron. All of these are mentioned. So now we know that h nu is given as 5 plus half mv square. So we have to use this particular formula. So we know that lambda is given, that is 4000 angstrom, which is nothing but 4 into 10 to the power of minus 7 meters. So we have E is equal to hc by lambda. So I can write it as 6.626 into 10 to the power of minus 34 into 3 into 10 to the power of 8 divided by 4 into 10 to the power of minus 7. So we have, when we calculate, we get 4.97 into 10 to the power of minus 19 joules. So now we calculate the energy. So we have 4.97 into 10 to the power of minus 19 divided by the charge on the electron, that is 1.6 into 10 to the power of minus 19. These both cancel out. We get 3.11 electron volt, because we need to find out the value in electron volt, and the charge of the electron, all of these are given in electron volt. So that's why this conversion is done. Now we can calculate what is the kinetic energy, which is given as half mv square. So we have half into mass of the electron, which is given 9 into 10 to the power of minus 31 into v square, that is velocity 6 into 10 to the power of 5 square. So we get the answer 1.62 into 10 to the power of minus 90 joules. So now let us calculate again kinetic energy in terms of electron volt. So 1.62 into 10 to the power of minus 19 divided by 1.6 into 10 to the power of minus 19. So these both cancel out. So we get 1.01 electron volt. So finally, we need to find what is phi. So energy minus kinetic energy. So we have energy that is 3.11 and then we have kinetic energy that is 1.01. So you get the answer 2.1 electron volt. So we have option B as the right answer. Next, question number 18. Which of the following is dependent on temperature? So we have molarity, mole fraction, weight percentage, as well as molarity. We know that molarity is mainly, it involves volume of the solution in the denominator. So we know that volume changes with temperature. So of course, it is the molarity which changes with temperature, or it is the concentration term which depends on temperature. Next, question number 19. A solution of sodium sulfate contains 92 grams of Na plus ions per kilogram of water. The molality of Na plus ions in that solution in mole per kg is very simple. Now we know that the mass of Na plus ions is already given, that is 92 grams. Next, molar mass of Na plus ion. So we know that it is 23 gram per mole. So we need to find the number of moles because molality is nothing but the number of moles of the solute divided by the mass of the solvent in kg, right? So we have, let us calculate moles of Na plus. So given mass is 92 by molar mass is 23. So we have 4 moles, right? So moles we have. Now we need to find out in 1 kg of water how much is present. Now you see here 92 grams of Na plus is present per kilogram of water. So already it is present in per kg of water. It is already mentioned. So this itself gives you the molality. So molality is number of moles of the solute in 1 kg. So already it is given as 1 kg. You have to divide it by the number of kgs of the solvent. So already it is mentioned that it is 1 kg of per kilogram of water. So molality is nothing but equal to 4. So we have option B as the right answer. That is 4 molal. Next, question number 20. In water saturated air, the mole fraction of water vapor is 0.02. If the total pressure of the saturated air is 1.2 atmospheric pressure, the partial pressure of dry air is. So first of all, let us calculate. Let us write the mole fraction. What is given here is mole fraction of water vapor. So this we already know, it is given. So X of H2O mole fraction, it is 0.0. This is given as a data. Now, total pressure, that is nothing but the P total is equal to, it is given as 1.2 atmospheric pressure. So this is the data that is given. Now, partial pressure of water vapor. So how do you calculate that? So partial pressure of water vapor is equal to vapor pressure, that is mole fraction of water vapor into the total pressure. So we have the mole fraction of the water vapor is 0.02 into total pressure is 1.2. So 0.02 into 1.2, we have here 2 into 2, 4 and 2. So we have 0.024 atmospheric pressure. This is the partial pressure of water vapor. Now, partial pressure of dry air, is equal to, so partial pressure of dry air, how do you find out? total pressure minus the partial pressure of water vapor. So total pressure is 1.2 minus partial pressure of water vapor, we have 0.024. So 1.200 minus 0.024, right? So we have 1 here, 6, 7, 1 and 1. So we have 1.176 atmospheric pressure. So we have the answer, that is option C, 1.176 atmospheric pressure. Next, question number 21. The mixture that forms maximum boiling azeotrope. So please remember this very important example under maximum boiling azeotrope, which is nothing but water and nitric acid. So option B is the right answer. Okay. Next, question number 22. If molality of the dilute solution is doubled, the value of molar depression constant Kf will be. So Kf is nothing but it is a property of the solvent only. It is a property of the solvent only, and it only depends upon the nature of the solvent. Okay, and it does not depend upon the solute concentration. Here they have given the dilute solution, the molality is doubled, right? So this is with respect to the solute. The concentration of the solute is changed. But as you should remember one thing, this Kf, which is a constant, the molar depression constant, it only depends upon the nature of the solvent. Okay, or as well as it also depends upon the freezing point of the solvent. So it does not depend upon the nature of the solute, the concentration of the solute. So here in this case, it remains unchanged. Okay, next, coming on to question number 23, the standard electrode potential E0 values of Al3 plus couple, Al couple, Ag plus Ag couple, K plus K couple, as well as Cr3 plus Cr couple are minus 1.66 plus 0.80 minus 2.93 and minus 0.74 volt respectively. Now you have to write it in decreasing order of reducing power of the metal. Now very simple, this is also with respect to the concept. So more negative is the E0 value, greater is the tendency to lose electrons. This is one basic rule you need to keep it in mind. So if the E0 value is more negative, then the tendency of that particular metal to lose electron is also higher. So now if we are writing it in terms of the negative value, so we have here minus 1.66 plus 0.8 minus 2.93 minus 0.74. So minus 2.93 is the highest, which corresponds to K plus K. So that is minus 2.93. So which is the highest. Next negative value is for the first one, that is Al3 plus Al, which is equal to minus 1.66. This is in terms of volts. Next is for the last one, that is chromium, Cr3 plus Cr, which is minus 0.74. And then we have the Ag, right? Ag plus Ag, which has a value of plus 0.8 volt. Okay, so now it is very clear that for potassium it is maximum. So we are only going to look into option B and C. Then it is for aluminium. Then we have chromium and the least will be Ag. So we have option B as the right answer. Next, question number 24. The correct order of reduction potentials of the following pairs is. So in this case, you can remember the values. So I'll just give you the values, or you can just look at the species and decide. So first I'll be giving you the values. Here it is plus 1.36 volt. Here it is plus 0.54 volt. For Ag, just we have written it is plus 0.80 volt. For Na plus, we have minus 2.71 volt. And for lithium, we have minus 3.04 volt. Li as well as Na. So both of them, they always try to undergo oxidation by losing electrons, right? So Na always tries to become Na plus, Li tries to become Li plus. So what happens here is, so in this case, now you look at these particular redox couples. So when I compare Li and Na, of course, look at the values also. Lithium has a very high tendency to lose electron and become Li plus. Now the question is with respect to the reduction potential. So they are asking which one of them undergo reduction by accepting electron very easily. Look at the values. This is 1.36, 0.8, and here it is 0.54. So next to chlorine, it will be Ag. So we have A maximum. In all of the options, we have A as maximum. Then it should be Ag. Okay, so we have C, right, in both of these. And then we have B, right? So in option A and C, we have this particular order. So I'm going to remove option B and option D. Now, finally, look at these two values. This is -3 and this is -2. So comparatively, sodium will be better, right? It will have the better order, higher order when compared to that of lithium. So we have next D and E will be the least. So we have option A as the right answer. Number 26, at 298 Kelvin, the standard electrode potentials of Cu2 plus Cu, Zn2 plus Zn, Fe2 plus Fe, and Ag plus Ag, the given values have been given. That is 0.34 volt, minus 0.76 volt, minus 0.44, and 0.80 volt respectively. So on the basis of standard electrode potential, predict which of the following reactions cannot occur. So again, we need to use the E naught. So E naught cell is equal to E naught cathode minus E naught of anode. So we have for the first one, if you are considering, that is for A. So copper sulfate plus zinc gives ZnSO4 plus Cu. So for CuSO4 and zinc, this particular couple, we need to take at the cathode, we have 0.34 minus the reaction at the anode is for the zinc. So minus 0.76. So 0.34 plus 0.76 gives you 1.10 volt. So it is plus. So that's why it is this particular reaction can take place. So this reaction occurs. Next, coming on to option B. So again, we are calculating what is E naught cell. So for copper, we are taking 0.34. And for the iron couple, we are going to take minus 0.44, which is already given in the question. So we have 0.34 plus 0.44, which is equal to 0.78 volt. Again, it is plus. So this reaction also can take place. Next, for the third one, we have for iron as well as zinc. So for iron, I'm going to take in the cathode. So minus 0.44. Now in the anode, it will be zinc. So minus 76, right? So based on the reduction potential, so we have here, it is 0.32 volt. So again, this also can take place. Coming on to option D. So here we have copper and Ag. So Ag has a better reduction potential. So I have to take copper in the cathode. So 0.34 minus. So in the Ag, that is 0.80, which is positive. 0.80, that is plus 0.80. Now 0.34 minus 0.80 will give a negative value. That is minus 0.6 volt. So since it is negative here, this particular reaction cannot occur. Next, coming on to question number 27. Which of the following reactions is an example of a redox reaction? So here we need to see where there is change in the oxidation number with respect to the reactant and the product. Then only we can call it as a redox reaction. So which is an example of a redox reaction? It is being asked. Now look at this particular first option. So we have xenon, here F6. So this will be in the +6 state. Now here, this is -2, -4. So xenon is again in the +6 state. There is no change in the oxidation number. So this cannot be the redox reaction. Here also it is in the +6 state. Here you can check this is -4 and -2. So of course this will be in the +6 state. Here also there is no change in the oxidation number. So it is not a redox reaction. Look at this particular example. Here it is in the +4 state and here it is in the +6 state. So it has been, the oxidation number has changed. So we have option C as the right answer. So here also you can check. So here also there is no change in the oxidation number. So that's why we are not going to consider it as an redox reaction. Here it is very clear that option C is a redox reaction. Next, coming on to question number 28. Which of the following reactions are disproportionation reactions? So here also you need to check where as I've already explained, in terms of reactants and the products will have the oxidation number more as well as less. So the reactant oxidation number will be in between the two oxidation states that are present in the product. So copper, you can see here it is +1 and in the product it is +2 and 0. So +1 is in between +2 and 0. So obviously 1 is a disproportionation reaction. Next, coming on to 2, let us calculate. So here manganese is X. So X minus 8 is equal to -2. So X is in +6 state. Look at the products. So here X minus 8 is equal to -1. So X is equal to +7. Here X is equal to +4. So 6 is in between 7 and 4. So this is also a disproportionation reaction. Let us look into this particular example. Here +1, X minus 8 is equal to 0. So X is equal to +7, right? So here +2, X minus 8 is equal to 0. So X minus 6 is equal to 0. So X is equal to +6. Here X is equal to +4. But now you can see that the reactant has the oxidation number 7, but in the product it is +6 and +4. The oxidation state of manganese in the reactant is not in between the oxidation states of manganese in the product. So this cannot be considered as a disproportionation reaction. And without going into detail, you can easily select this particular option, which is not a disproportionation reaction, because already in the reactant, manganese is in its highest oxidation state. So it cannot undergo disproportionation reaction. Now, in this particular reaction, that is 4, you can see manganese there are 2 reactants with manganese and only 1 in the product which contains manganese. So obviously, this also cannot be a disproportionation reaction. So we have only 1 and 2. So option B is the right answer. Next, question number 29. Oxidation number of chromium in Na2Cr2O7 is. So for Na, it is +1. So 2 are there. Now chromium is X. So let us take it as 2X. Oxygen is -2. -2 into 7. So 2 plus 2X. So this is equal to 0 anyways, right? So -14 is equal to 0. So 2X minus 12 is equal to 0. Or 2X is equal to 12. X is equal to +6. So we have option C, that is +6 as the right answer. Next, question number 30. A solution is prepared by dissolving 0.6 gram of urea, molar mass 60 gram per mole, and 1.8 gram of glucose with the molar mass that is given 180 gram per mole in 100 ml of water at 27 degrees Celsius. Now, osmotic pressure of the solution is asked. So now, let us start with understanding about. First, we have urea that is dissolved. The mass is given mass is there, molar mass is there. From this, what we can find out? We can find the number of moles. So first, let us find number of moles of urea. So given mass is 0.6, molar mass is 60. So we have 0.01 moles, right? Next, we can also calculate the moles of glucose, number of moles of glucose. So given mass is 180 and molar mass is, given mass is 1.8, molar mass is 180. So we have again 0.01 mole. So from the given data, these two things can be easily calculated. Now let us calculate. Now they have asked the osmotic pressure of this entire solution, which contains both urea and glucose. So let us calculate the total number of moles. So total moles of the solute in the solution will be 0.01 plus 0.01, which is nothing but 0.02 moles. Now, how do we find the molarity? Because for osmotic pressure, we are using molarity as the concentration term. So molarity is number of moles of the solute divided by volume of the solution in liters. So we have number of moles, the total moles we are going to take, that is 0.02, and how much of, 100 ml of water. So we have to write the volume in liters. So 100 ml in liters will become 0.1 liters. So we have 0.2 mole per liter. This is the concentration. Now we know that pi is equal to CRT. C is nothing but the molarity. So pi is equal to, the molarity is already we know it is 0.2 into R is given 0.08206 into the temperature. Now 27 degrees Celsius is given. It has to be converted into Kelvin scale. So 27 plus 273, which will give you 300 Kelvin. So we have 300. So when you do the substitutions and calculate, you're going to get 4.92 atmospheric pressure. So we have the answer option C, that is 4.92 atmospheric pressure. Next, coming on to question number 31. K2HgI4. So this particular compound is 40% ionized in aqueous solution. The value of its Van 't Hoff factor, that is I, is asked. Okay, so now let us look into this particular compound. We know that there are 3 ions that are formed. So 3 ions are formed by the dissociation. So also the alpha is given, that is 40% ionized. So that means, which is nothing but alpha value is 0.4. So we have I is equal to 1 plus alpha n minus 1. Now here n is 3 because there are 3 particles per molecule of this particular compound. So 2K plus ion and the anion that is present. So we have this particular equation to find whenever it is the particular compound is undergoing dissociation and the number of particles are more in the compound than in the solution than expected. So while substituting, we have I is equal to 1 plus alpha is 0.4 and then we have n is 3 minus 1. So we have 1 plus, now we have 0.4 into 2, which is nothing but 0.8. So 1 plus 0.8 will give you 1.8. So we have option A as the right answer. Next. Question number 32, assertion, zinc displaces copper from copper sulfate solution. This we already know. Yes, because here zinc plus Cu2 plus will give you Zn2 plus Cu. This is the right statement. Now, here you have to see the standard electrode potential E0 at 298 Kelvin of zinc is minus 0.76 and that of copper is 0.34 volt. So please remember these two standard values for zinc couple as well as for copper. For zinc, it is minus 0.76 volt and for copper, it is plus 0.34 volt. So we can also calculate the E0 cell, that is E0 cathode minus E0 anode. So we have E0 cathode is 0.34 volt minus E0 of anode is minus 0.76 volt. So we have 1.10 volt, right? Because minus and minus, it becomes plus. So 0.34 plus 0.76 will give you 1.1 volt. So it is positive. So that means it is spontaneous reaction. This particular reaction is spontaneous. So assertion is correct. The reason is also correct. And reason is a correct explanation of the assertion because based on these values, we can tell that zinc displaces copper from copper sulfate solution. So yes, option A is the right answer. Next, coming on to question number 33, the decreasing order of electrical conductivity of the following aqueous solutions is. So we have, in this case, formic acid, all of these, it's the same, the concentration given is the same. So we have formic acid, HCOOH, acetic acid, CH3COOH, and benzoic acid, C6H5COOH. Now, in this case, we know that here in HCOOH, that is formic acid, there is highest degree of ionization. Why it is having the highest degree of ionization? Because it is compared to all the other carboxylic acids, HCOOH is the strongest acid because CH3OH, it has the alkyl group which is attached to the carboxyl group. So which again, it decreases the acidic character of this particular compound. And in the third example, that is the benzoic acid, in the third case, so there is a phenyl ring which is directly attached to the carboxyl group, which reduces the acidity, right? So we have the order in this way. So HCOOH is maximum, then it will be acetic acid, then it will be benzoic acid. There was the decreasing order of electrical conductivity. So for A, it will be maximum. So I'm going to remove these two. Then it will be B and then it will be C. So we have option C as the right answer. Next, question number 34. The number of electrons delivered at the cathode during electrolysis by a current of 1 ampere in 60 seconds is. Again, here it is a simple calculation with the substitution. So Q is equal to IT. We have this equation. So I is the current, that is 1 ampere. So I take it as 1. Time is 60 seconds. So we have 60 coulombs, right? So number of electrons have to be calculated. Number of electrons. So how do we calculate? So N is equal to Q by E. So here we have Q, which is 60, and E is the electronic charge, 1.6 into 10 to the power of minus 19. So we have 3.75 into 10 to the power of 20 electrons. These many electrons. So we have the answer, that is option C, 3.75 into 10 to the power of 20. Yes, we have next question number 35. The addition of a catalyst during a chemical reaction alters which of the following quantities? So again, it is very clear that whenever a catalyst is added, so the activation energy is lowered, right? So in a normal reaction, if you take the reaction coordinate, so this is the reactant. Product will have a lower energy than that of the reactant. So this is the energy and this is the reaction coordinate. So whenever you're adding a catalyst, what happens is the activation energy is lowered. So this energy gap is nothing but the activation energy. So this energy gap is lowered in the presence of the catalyst. So the correct answer is option C. Next, question number 36. Compound A contains 8.7% hydrogen, 74% carbon, and 17.3% nitrogen. The molecular formula of the compound is given. Atomic mass of carbon, hydrogen, and nitrogen are 12, 1, and 14 AMU respectively. The molar mass of the compound is. So you need to identify what is the right molecular formula of the compound. So now, let us write the element, and then we have the mass, and then we have the number of moles. So we have the three elements, carbon, hydrogen, and nitrogen. Hydrogen and nitrogen. Now for carbon, how much is there? It is given as 74. Hydrogen is 8.7 and nitrogen is 17.3. Now number of moles is given mass by molar mass. Molar mass of carbon is 12. So 74 by 12. We have 12. 6 are 72. 2 remains. So then we have 12 ones are 12. 8 remains and 0. Then we have 6 are again. We have 72. 8 remains. And then it goes on, right? So it becomes 1666. So I'll write it as 6.167. 167 moles. Next for hydrogen, we have 8.7 divided by 1, which is nothing but 8.7. Then we have for nitrogen, 17.3 by 14. We have, so if I shift the point, so 173, 140, ones are 140. So we have 3 here. So point 140, again it comes to 2, right? So 280. So 5, then it becomes 0 again. So it comes to around 3. So I'll write it as 1.23. I'll remove this calculation part. I'll just erase this. So we have got the number of moles now, but it is not in whole numbers. So what we need to do is we need to divide all these numbers with the smallest number. So we have the smallest number, that is 1.23. So you're going to divide for carbon, that is 6.167 divided by 1.23. Next, we have for hydrogen, 8.7 divided by 1.23. And then for nitrogen, 1.23 divided by 1.23. So now we are almost getting the whole numbers. You need to get the whole numbers here, 1 and 1. So it becomes 1 anyways. Now here 1.23, and here in the numerator we have 8. So it is almost 7 times. Here 6 and 1 we have 6.1 it is, here 1.2. So it is 5, right? So we have 5, 7 and 1, that is carbon 5, H7 and PN1. Just by approximations, you can easily get the whole numbers. Don't go to divide in detail. Okay, so now what else is given? The molar mass of the compound is given. So for that sake, we need to find out the molar mass of this particular formula, what we have got. So the empirical formula that we have got. So 12 into 5 is 60. H7 Next, nitrogen is 14. So we have 60 plus 7 plus 14, that is 81. So molar mass is given as 162. So we have N is equal to 162 by 81, which is nothing but 2. So that means I have to multiply the entire empirical formula by 2 to get the molecular formula. So it will be C10H14N2. So we have, yes, C10H14N2. That is option D as the right answer. Next, question number 37. The standard heat of formation of Ba2 plus aqueous, this particular ion, in kilocalorie per mole is. So they have given the standard heat of formation of sulfate ion, standard heat of crystallization of barium sulfate, and standard heat of formation of barium sulfate. So now, first of all, we know that Ba2 plus aqueous plus sulfate aqueous gives BaSO4, that is in the solid state. Right. Now for this is nothing but the crystallization. So we know that delta H of crystallization, it is given as minus 4.5 kilocalories per mole. So now delta H of formation of BaSO4 will be equal to delta H of formation of Ba2 plus delta H of formation of SO4 2 minus plus delta H of crystallization of this particular compound. Right. Now, here delta H of formation of barium sulfate is already given, heat of formation, that is minus 349 kilocalories per mole. Now, delta H of formation of barium, that is what you need to find out, the standard heat of formation of barium ion. So let us keep it as such, delta H naught of formation of barium ion, Ba2 plus ion. Now for sulfate, how much is it given? Yes, heat of formation is given minus 260 plus for crystallization, it is given as minus 4.5. So I can write it as delta H naught of formation of Ba2 plus is equal to, now we have here, let me keep this particular thing in the same side. I take all of them to the other side. So I have minus 349 plus 260 plus 4.5. So 216 plus 4.5 comes to 220.5 minus 349 will give you minus 128.5 kilocalories per mole. So we have the answer, that is option B, minus 128.5 kilocalories per mole as the right answer. Okay, so I hope you understood how we have to take the equation. So they have asked how much is the energy that is required for the formation of Ba2 plus. So we are going to take it in the form of the equation where delta heat of formation of barium sulfate, that is equal to the delta heat of formation of barium ions and sulfate ions, and then the crystallization, right? So with these ions, the final crystallization also has to take place to give you the barium sulfate, the salt that is there. So this particular the delta heat of formation of barium sulfate includes all of these different quantities which have to be added up. So then we get this particular answer, that is option B. Next, question number 38. Consider the following compounds. The oxidation state of the underlined elements in them are respectively. So here K2O2. So this is 2 minus. This is a peroxide. So peroxide is O2 2 minus. So here K2 will have 2 plus. That means K plus K, if you're talking about 1K, okay, so K will have only plus 1 charge. So potassium will have a plus charge. So 2 potassium atoms will have 2 plus charge. So 1 potassium will have only 1 plus charge. So we have plus 1 here. Next, H2O2, again it will be, see here underlined atom is oxygen. So O2 2 minus, it is in the peroxide state. But we are finding out what is the oxidation state of 1 oxygen. So it will be minus 1. So here we have minus 1. Next for sulfur here, plus 2. X plus oxygen is minus 8 is equal to 0. So we have X minus 6 is equal to 0. That means X is equal to plus 6. So we have plus 6. That is option B is the right answer. Next, question number 39. If the half-life T half for first order reaction is 1 minute, then the time required for 99.9% completion of the reaction is closest to. Now, again, it is given as first order reaction. So T is equal to 2.303 by K log of A by A minus X. Now, T half is given as 0.693 by K, which is equal to 1 minute. So T half is already given as 1 minute. Now, K is equal to, so you have 0.693 per minute, right? Here I can write it as K is equal to, this minute comes here, so minute inverse. So from this, we have the value of K. Now, 99% completion means 1 point, now this is 100, A is 100, A minus X will be 99.9 has been completed, so remaining amount is only 0.1, right? So let us substitute T is equal to 2.303, K is already there, 0.693, log of A is 100, A minus X is 0.1. If I shift the point here, this side and here, we have log 1000. Log 1000 is 3, right? So 2.303 into 3 divided by 0.693 will give you, so here we have almost equal to 9.97, which is equal to 10 minutes. So we have the answer, that is option A, that is 10 minutes. Now, without doing the calculations also, you can easily remember the formula. I have explained this while explaining the chapter of chemical kinetics, in which I have told that whenever you're comparing the half-life as well as when you're talking about 99.9% completion of the reaction, you should keep it in mind that the relation between the half-life and this particular time is that it is 10 times the half-life. Okay, so the time required for this much of completion of the reaction, 99.9% completion, is 10 times than that of the time required for 50% completion. That is the half-life for first order reaction. So you can directly take it as 1 into 10, that is 10 minutes, instead of going for all these extra calculations. Next. Question number 40. Uric acid ionizes in 3 steps with ionization constants K alpha 1, K alpha 2, and K alpha 3 respectively, while K alpha is the overall ionization constant. Which of the following statements are true? So when I write K alpha, it is K alpha 1, K alpha 2, and into K alpha 3, which is the right statement. Now, when I take the log of this, I can write it as log K alpha is equal to log K alpha 1 plus log K alpha 2 plus log K alpha 3. Now, look at the options that have been given. See, K alpha is equal to the product of all of these ionization constants. So if I take log of that, so I get log K alpha is equal to the sum of all of these ionization constants. So option A is correct. So option A is here, A is here, and A is here. So I can remove this option. So So next, coming on to H3PO4 is a stronger acid than H2PO4 minus and HPO4 minus. Yes, obviously, when I'm talking about H3PO4 and then comparing with H2PO4 minus, here the removal of the proton is easier when compared to that of removal of proton from H2PO4 minus, because it already has a negative charge. Now removal of one more H plus is quite difficult when compared with that of the H3PO4. Now, again, when I take HPO4 2 minus, you can easily see that here there are two negative charges. So removal of that H plus is too difficult compared to the first two cases. So this is the proper order. So we have the option B also. This particular statement, this particular relation is also correct. So B is also correct. So we have B here, B here. Okay. Next, let us look into the option C, what is given. So K alpha 1. So yes, phosphoric acid, when you're talking about ionization constants, so obviously the K alpha 1 will be greater than K alpha 2, which is greater than K alpha 3. So this is also correct in case of polyprotic acids. This is the right statement. So C also is correct. Right? So we have A, B, and C. All of them are correct, whereas there is no particular relation as such, which was given in option D. So we have option A, where A, B, and C only. All of these are correct. So option A is the right answer. So next, coming on to question number 41. Which of the following aqueous solutions will exhibit the highest boiling point? So we have the equation delta TB is equal to I into KB into the molality. So in this case, when we are talking about, let us talk about I, right? So in this case, in the first case, I is equal to 1, right? And this does not undergo dissociation or association. So I will be 1. Now, when I'm talking about the concentration, it will be 1 into 0.015, which is equal to 0.015 molality, or just I'll write the concentration just as such. Next, here we have 0.01 molar urea. Here also I is equal to 1. So again here the concentration will be 0.01. Okay. Next, talking about KNO3. Here the I is equal to 2 because two ions are formed, K plus and NO3. So I have to multiply this concentration by 2. So I have 0.02. Here Na2SO4, I have two Na plus ions and sulfate ion. So I is equal to 3. So here the concentration is 0.03. So compare the concentrations. Here it is very clear that the concentration is directly proportional with that of the boiling point. So, and it is also a colligative property. So the elevation and boiling point will be directly proportional to the molality of that particular solution, or the number of particles of the solute that is present in the solution. So it is very clear that this particular 0.01 molar Na2SO4 solution will have the highest boiling point. Next, coming on to question number 42, Dalton's atomic theory could not explain which of the following. So it is very clear that it could easily explain the law of conservation of mass, law of constant proportions and multiple proportions, but it could not explain the law of gaseous volumes, which was later taken into consideration under Gay-Lussac's law of gaseous volumes. Next, question number 43, higher yield of NO. So they have given a particular equation. So you have to see N2 plus O2 gives 2NO. They have given the conditions where delta H is plus 180.7 kilojoules per mole. That means the reaction is endothermic. Heat is absorbed during the reaction. If it was minus, then we could say it is exothermic, but here it is endothermic in nature. Now, if it is endothermic, we know that if temperature is raised, of course, the reaction proceeds faster. So higher temperature, then higher yield of NO will be formed. Lower temperature, it will be opposite. So this cannot increase the yield of NO. Next, higher concentration of NO. So if you increase the concentration of the products, then what happens? The reversible reaction will take place, the opposite. The opposite reaction will take place and more reactants will be produced. The reverse reaction takes place. So this will not increase the yield of NO. Higher concentration of O2, yes, of course, the reactant concentration, if you increase, more and more reactants can combine to form the product. That is, NO is a product. So when A and D, okay, in case of these conditions that is mentioned in A and D, then the yield of NO will be more. So we have option B as the right answer. Next, question number 44, match list 1 with list 2. So in case of humidity, so look at the various types of solutions they have mentioned. So humidity is where the liquid is dispersed, which is present in the air, right? Or in the gas. So we have liquid in gas. So for A, we have 2. Right? Next, so I can easily remove this option A and option B. Next, alloys. Alloys are also called as solid solutions. So both are in the solid state. Like we have examples like stainless steel, brass, right? So or bronze, all these are alloys, which are solutions of solids. So solid and solid. So for B, we have 1. So we already have the answer, that is option C. Next, amalgams. So we have simple examples of the sodium amalgam, right? Which we have come across in organic chemistry also. So we have, in case of amalgams, we have this liquid in solid, that is C44. And then finally, smoke is nothing but the solid that is present in the air or in the gas. So we have D for 3. So option C is the right answer. So finally, coming on to the last question of today's video, the osmotic pressure of a solution is directly proportional to. So we have the equation pi is equal to m or CRT, I'll just write because m, small letter m is for molarity. Here we are taking molarity. So CRT, C is nothing but we express the concentration in terms of molarity. Okay. So we have here pi is directly proportional to temperature, but here it is given as temperature only. So let us look into the other options. Molarity only, no. Molarity and temperature, yes. So option C is the right answer. So with this, we come to the end of this particular video, that is video 9 of the PYQ series. So I'll be coming up with one more video, that is video 10, again based on physical chemistry questions. So I hope this video is helpful and I hope your confidence has been increased with respect to solving questions on this physical chemistry. So thank you so much for watching the video. Subscribe my channel for more such chemistry related informative videos. Thank you.